I'm Carson Beislein.
I'm William Dickstein.
I'm Marnie Malone.
I'm Zoe Nix.
And I'm Katie Whitehead, and this is our Group 4 final design project.
We're going to start off with some background info on Iceland's energy and electricity use. So for population, Iceland's population as of 2021 is about 376,000 people. And total electricity consumption is a little shy of 19.5 billion kilowatts per hour, or kilowatt hour per year, with its main sources of electricity being hydro, which it takes about the majority being 69%, geothermal coming in second with 30%, and then wind and just 0.01% for fuel. So most of their energy is coming from renewable sources. Their electricity use per capita is about 48,000 kilowatt hours per capita. For total energy, the total energy consumption is about 55 kilowatt hours per year, with the uses of energy, majority being electricity, transportation, heating of residents, a lot of times through a geothermal source, but otherwise with electricity. Industry, they do a lot of smelting of aluminum, and then Bitcoin mining, which we'll talk about later. But our country to compare with was Canada. So their energy use per capita was 87,000 about kilowatt hours, and Iceland is a lot more, being 167,000 kilowatt hours. But as William's about to talk about, it is kind of canceled out because Canada uses a lot more non-renewable energy.
So here's one thing I want you to keep in mind. Iceland is one of the highest energy users per capita across the entire globe. They use almost double the amount of energy per person per year than Canada, which is another industrialized country where people enjoy roughly similar standards of living. However, that relation is inverse when you talk about per capita CO2 emissions. Even though Iceland uses a lot more energy, Canada emits a lot more carbon dioxide. Per person, Canada emits about 14.4 tons per person per year, while Iceland only emits 8.6 tons per person per year. That is a remarkable change. And the reason why is that Iceland's grid is very reliant on renewable energy, specifically hydropower and geothermal energy. In fact, in total, Iceland's carbon emissions are only 2.95 million tons of carbon per year. That is very little compared to other Western industrialized countries. So what if we considered Iceland as though all of its electricity came from coal-fired power plants? Coal is notorious for emitting a lot of carbon dioxide per energy emitted. So if Iceland was entirely powered by coal, instead of emitting 2.95 million tons of carbon dioxide per year, it would emit around 19.7. That is around a 6-fold increase in the amount of carbon emitted. And accordingly, their emissions per capita would rise from about 8 tons to around 52 tons per year. That is a massive difference. It's also much higher than Canada's current carbon footprint. If you adjusted Iceland's carbon footprint, it'd be 52 tons. Canada currently is only around 14.2 tons. This difference is due to a couple factors. One, Canada just uses less energy. And two, if coal is extremely CO2 productive, so if Iceland moved entirely to coal, it would emit a lot of carbon dioxide. For example, if Iceland were to move over to natural gas, they would emit a lot less tons of carbon dioxide per year. Preparing for the future. So Iceland expects a lot of change. Their population has been on a rapid increase, and we wanted to model what would happen if the population of Reykjavik increased 40% over the next 20 years. So If the population increased by 40%, first, that would mean the population of Reykjavik would increase by around 55,000 people. That would take the population of Iceland to around 430,000 people. We predict that electricity demand would increase by around 2.61 terawatt hours per year, going to a total demand listed above. Once the number of people increase, you're going to need a lot more heating in houses in order to keep them warm, especially during the cold Icelandic winters. We predict that around a 1 terawatt hour per year increase will be needed for this new population. In addition, this new population is going to be heating water for use in their daily lives. We predict that there's going to be need to be an increase of around 231 megawatt hours per year in order to heat water for this new population. That's around 7 million tons of heating water per year.
Bitcoin mining. Currently, Bitcoin electricity usage in Iceland is 840 gigawatt hours per year. However, we're going to assume a 50% increase in mining due to the attractiveness of companies because of the low energy cost. And the new electricity demand would then be 1,260 gigawatt hours per year, and netting an overall increase of 420 gigawatt hours per year. And then subsequently making the total energy demand in 2042 projected to be 4.85 terawatt hours per year.
So now that we have our total increase in energy use that we're going to need, we are going to design a hydroelectric power station to fit that increase and also all of the Bitcoin electricity use. So some assumptions and knowns that we have before we dive into the calculations. For all of our calculations for the increase, we calculated them by assuming that the per capita values for electricity, space heating, water heating, and Bitcoin is going to stay the same over 20 years. This was the only way to make an accurate prediction of what the numbers were going to be. And so our values for energy comes from that, and we'll be using that in our calculations for hydroelectric power. We are also assuming values of efficiencies based on existing plants, and these are existing hydroelectric plants. So the numbers that we found from our research were that the electricity transmissions efficiency is about 97%, space heating efficiency is actually 100%, and the hydroelectric station efficiency is 90%. So we're going to use all of these efficiencies in our calculations and make sure we take them into account. We're also assuming from the problem that the height of the dam is 50 meters, and we are also assuming that space heating, water heating, all types of heating are provided from electricity. So this is kind of an overview of our calculations. First, we did it by looking at space heating and taking that efficiency. The next step was looking at electricity. So since space heating and heating water is all from electricity, we took our total electricity need and divided that by our efficiency of electricity transmission. That gave us our total power needed to be produced from the plant, and that's that 5 terawatt hours. And from there, we were able to solve for the volumetric flow rate using our mass flow rate and our density of water. So we finally found that our volumetric flow rate for our hydroelectric power station would need to be around 1,300 meters cubed per second. So this is just kind of an overview. Again, we found that it's around 1,300 meters cubed per second with that 90% efficiency of the plant. And our needed produced power is the 5.7 times 10 to the 8th, which was just calculated from the numbers that we had previously stated. And so looking at our feasibility, the waterfall that we were supposed to do research on was Öxarárfoss. Unfortunately, we did a ton of research on it and could not find a solid volumetric flow rate anywhere. We found one source that had it at the flow rate at 1 meter cubed per second, and that just didn't really seem very accurate. We also reached out to the national park itself to ask them, but we weren't able to get a response back in time. But based on different flow rates known from waterfalls in Iceland, we do know that it is less than 150 meters cubed per second. So ultimately, we decided that this power plant is not feasible just because the volumetric flow rate is too large to be driven by just one waterfall in Iceland. Technically, Gullfoss has an average flow rate higher than this at about 1,400, but that is just during the summer and would be unsustainable year-round. So realistically, the plant would either need to have the dam be taller or have the power demand be split up among multiple plants.
The geothermal power station utilizes a binary cycle.
First, we're going to talk about the proposed location. So we found that Selton is a pretty close vicinity to Reykjavik, 40 kilometers. And this would be great for using it for all the houses there, as well as the Bitcoin mining, tourist attractions, the increase in electrical vehicles, etc. This is a really popular geothermal site that has a lot of geothermal heat from it.
The binary cycle power plant utilizes 3 fluids in conjunction with each other to produce the net output power. Firstly, geothermal fluid with energy and heat flows into the heat exchanger, which then gives energy to the working fluid of the cycle. The working fluid is commonly butane, pentane, or R404, for example. This working fluid is then converted to steam, where through the steam turbine, the steam turns the turbine to create mechanical work and then subsequently spin a generator. The working fluid then exits the steam turbine and flows through a condenser where a cooling fluid, we used water, reduces the steam back down into a liquid where the working fluid is then pumped to cycle again. For concluding the input and exit temperatures and mass flow rates of the geothermal fluid and the cooling fluid, we utilized an Excel spreadsheet which analyzed our requirement and then the subsequent input and output values, which then allowed us to compute our efficiencies. So our main equation of analysis was the power equals the mass flow rate times the specific heat times the change in temperature, where the input power from the geothermal fluid was found to be 1,200 kilograms per second times a specific heat of 4184 and a change in temperature of 80 degrees. This resulted in an input power of approximately 401 million joules per second. And the waste power was then computed to be approximately 350 million joules per second with the same equation. With a desired power output of 571 million joules per second and the net power output per well and turbine to be 51 million joules per second, we needed approximately 12 wells and turbines to obtain our desired power output. And this is assuming each well has its own respective turbine. There are no significant losses in the heat exchangers, and there are no significant losses in the electrical power generation. The effectiveness and efficiency calculations. The efficiency is equal to 1 minus the output power, or the power transmitted to the cooling fluid, divided by the input power, which is the power coming from the geothermal energy. And we concluded that our cycle's net thermal efficiency was 13%. And then the second law of effectiveness involves using exergy. And the equation for exergy is shown on the left side. And which is in the second law of effectiveness was one minus the energy wasted divided by the total exergy output, which was found to be 46.3%.
So next we will discuss the stakeholder analysis. We grouped our stakeholders into three main categories. On the next slide, we can see the first group has the most involvement and are most invested in the project. And all of these groups have a lot to gain from the power plant being built. So first up, the power plant project team. Of course, it's their job to get the project built. And then the Bitcoin mining company will also be benefiting directly from the energy produced by the plant for mining. And then Icelandic energy companies as well will be profiting from the higher energy production to sell to consumers. And then our second group in the middle maybe aren't as directly involved, but have some power in the project and are still going to be largely impacted by it. The original landowners will be involved in the sale of the land, but probably not involved afterwards. And then Icelandic politicians and cultural heritage experts both will have some say in the land regulation and if it would be an appropriate site for the construction of our power plant. And then finally, Icelandic farmers and environmental groups will probably both have concerns over the effects of construction on the land, whether it impacts crops or local ecosystems. And they might also have some say in addressing those concerns. And then finally, the last group on the right includes people who may receive some of the energy provided by the plant, and in which case it might be a benefit for them, or they may see it as a nuisance because of noise or smell disruptions from construction. So that would depend on the perspective and who you ask. And then those include Icelandic residents, tourists, schools, parks, swimming pools, businesses, and electric vehicle companies. So for our focus groups in the stakeholder analysis for the Dagerfoss power plant, there were some mixed opinions on the plant. Of course, first up, Icelandic politicians will be able to regulate how and where the power plant is built. And they'll also be able to voice public support, either for or against the project. And so several politicians have advocated support for expanding renewable energy and receiving economic benefits from it. But a lot have also expressed concerns about its environmental impact. It is also, oh, sorry, can you go back? It is also in the interest of Icelandic energy companies to assist with this project since they stand to profit from increased energy production. They have like a lot of economic power to support kind of expanding renewable energy consumption and increasing their profit. And then Icelandic farmers will likely not have as large of an influence on the project, but they will of course have valid concerns if there is a harmful impact on their crops or livestock. And the power plant coordinators will have to take into account making sure that they can maintain their farmland and provide for themselves. And then we went more into depth on the Icelandic environmental groups for our presentation. So on the next slide, we talked about how environmental groups will have less influence on the project itself, but similarly to farmers will still have concerns, in their case, protecting wildlife and natural habitats is also important to consider. Next slide. So some of the impacts that environmental groups will face before construction, they may be organizing campaigns and meetings to discuss the environmental impact of the power plant. And then after construction, they will be impacted by changes in land condition and whether they accept the energy production being produced. So this concludes our presentation, and a full list of our sources can be found in our written report. Thank you.